I can be the cameraman. I can like pan and zoom and focus for you.
Yeah, no, we don't need that. But if you could double check and make sure that's good. And then we'll set up bounds. All this garbage will go on the video, because I'm not going to edit. Tell me how far to the left can I go? Tell me when to stop.
Pretty much that line.
Ah, cool.
Except for when your laptop rotates.
It's hard because it's not level.
All right, so the hope today is to go through 2 problems doing finite Fourier transforms. Is that what they're called in this class? Or eigenvalue expansion?
Finite Fourier transforms is like what you labeled the title.
Okay, cool. So that's what we'll call it. I'm going to do a 1 in 1 and a 2 in 1. So that's 1 spatial dimension and 1 time dimension, and then 2 spatial dimensions and 1 time. So the first example I lifted from a book. The second one we're going to just make up and hopefully solve. All right, so one more time, Colin, is this visible?
Ask Megan. Wait, Colin's gonna now have a female voice. Go.
It looks decent to me. A little blurry, but that could just be like resolution.
That's
low
I'm not.
I'm
Camera.
going to upload all these notes online anyway.
Okay.
So this is just du dt, d squared u dx squared, plus e to the minus t, 3 sine x. This is our governing equation. And our bounds on x are 0 to pi. And then we have some, we're going to need 1 initial condition and then 2 boundary conditions to solve this. So u at x equals 0 and t is equal to 0. And we can do u at pi and t is equal to 1. So you have this inhomogeneity. And then u of x for t is equal to 0, some f of x. I'm just going to leave it as that. We can maybe throw in a few different f of x's later on and actually solve for the coefficients that would come from that, but we don't care. We can, as long as we define, we can go from there. So maybe it might even be worth trying to plot all this crap in MATLAB when we're done too, because I think that's important, especially when you're in these radial systems, when your answers are Bessel functions, and you're like, what the hell?
Yeah.
So you don't have a feel for it, so you don't know how to use them. So it's kind of garbage. So if we plot this, we got u, we got x, this is a pi, that's a 0. And all we really know for sure is that, if we assume there's a linear relation between these two things, we know the initial condition, or the boundary condition in time for any t is going to be something like this, right? There's no reason to assume it's linear, but what the hell? So you could solve this as a homogeneous solution, and then you can add it together using superposition and non-homogeneity into it, because you can break them apart like that. Or you can just shift it, because this is a linear, or this is just a scalar. We can shift all of our stuff over to this kind of equilibrium, and we can just say that this v of t is equal to ux of t minus x by pi. And that'll give us, at 0, this is 0, right? And then at pi, this becomes 1, so this is also 0. Does that make sense? So now our boundary conditions are v at 0, t is equal to 0, and v at pi and t is equal to 0. So now we can just do this homogeneous solution. And then, we shift this accordingly. We'll knock that off also, or we'll add that on.
So the idea is to solve it using that new v equation, and then you can at the end take it back to the original.
You'll just, it'll be
okay.
v plus this is equal to u.
Gotcha.
So this way you don't have to solve those two systems. So it's just a little bit less work. So
why don't they kind of give us this material in the course?
Huh?
Why isn't this really presented in the course?
because I'm here
Okay.
to present it to you.
But 5 people can't.
And that's why I think these recitations will be good for you, because hopefully if you get something like this on the exam, this is an easier way to go about the problems. Like, I think this is from Haberman, which I believe I've emailed to everyone here. No? Email me, I'll send you the book. Or you can download it illegally off the internet. Oh, I got it. All right, so we have this new cast. We have this new governing equation. Down there's our new boundary conditions. And we can go through all of our separation of variables and all that stuff. And you know how that looks now for if you have no forcing function here. So it's just this dv dx. So you get something that's like x double prime, for this is our x eigenvalue here, will equal something like lambda squared x equals 0. So you've done this a lot already, I'm hoping. This is kind of familiar, and I'm not going to go back through it. But that's just, you know, if you do separation of variables on this equation here, minus that, and then your t will have the similar stuff. So when you're going through these problems and you have radial coordinates, that's basically the same operation you're doing, and you'll have, you know, this 1 over r ddr times r dv dr would be your r stuff, and you know you'll have a theta component and all that. But that's all in your notes, so I wouldn't even worry about that. You can just kind of cut right to this. But this equation's good because it's going to come back and help you. So this is sines and cosines, right? And I believe there's a thing in your book, but we can just, you know, by inspection, we know what this is going to be now. Because it's got to be 0 at the origin and 0 at pi. So we know 0 at the origin is going to give us a sine. And then at pi means that we're going to have to do something that it's like sine, you know, our lambda is going to be something like n pi x. And you generally you divide this by the length of your domain. So a lot of the problems you do now is the length of the domain is 1. But if it was L for here, it's pi. So we get that it's just equal to sine of nx. And then this is our lambda n. So it's possibly the simplest eigenvalue that you can get for one of these problems. So we know that our solution to v is going to be equal to this summation from n equals 1 to infinity of a n of t, where that's our coefficient in time, times our eigenvalue. And this is just the form that you would expect. So what we're going to do now is we'll multiply our governing equation here by our eigenvalue, and we'll integrate over our domain. So it's nothing too drastic, right? So we have what? X, I'm not even going to put a sub n, times dv dt. I'm going to put a large gap here because I'm just going to do, well, whatever. Equals, oh, there's a dx, equals the integral 0 to pi of x dv dx squared dx, and then plus the integral 0 to pi of x times e to the minus t sine 3x dx. Right? So this isn't too bad. This one here is very simple to deal with, so we'll do it in 3 parts. We got 1, 2, and 3. The first integral is easy. X is strictly a function of big X, the eigenvalue, is strictly a function of X. So we can move that into this ddt. So we get something like, in ddt, the time derivative has no dependence on the spatial. So we can bring that to the outside, and we get something like xv dx, right? It's that whole derivative. Now, this is the definition here of the Fourier transform with respect to our eigenvalue x, right? So we could just call that for this rectilinear coordinate system. So we could just call this like v hat n. So that one's simple. 2, when you look at this, there's all spatial dependence here. So if it was, we have to worry about the dependence of the variable and how do these kind of derivatives work. But you can kind of see really quickly by inspection that we're going to be doing 2 integration by parts to remove the derivative off of our variable v, and we're going to try to place them onto our eigenvalue. And then our boundary conditions will be set by the kind of those constant terms from, or whatever you call those boundary evaluations that are in an integration by parts problem. So 2 is, we'll just do this really quick. And actually, I'm just going to write v prime prime, because we know it's a spatial derivative. I don't have to. So that's equal to what? xv prime. If I'm doing this wrong, just yell at me. Minus the integral 0 to pi of x prime v prime dx. And this thing is actually equal to minus x prime. You feel like I'm doing this wrong. X prime v 0 to pi plus the integral of x double prime v dx. All right, so that's right. So this is that weird staggering way that everyone writes. So now if we didn't do that shift all the way back here, where u at pi is equal to 1, u here at pi we would get a value, correct? And we could still use the same eigenvalues, but now we have this slightly messier differential equation is going to come out, because we're going to have a term here that's going to persist. But because we set that equal to 0, we know we can zero all this stuff out. So we'll just do all these evaluations. We'll go here, here, and then we'll worry about this guy. Our eigenvalue was set up to be homogeneous on our bounds. So we know that these are both zeros due to this. So that's going to go, that goes away and that goes away. V is our boundary condition, which we know is going to be homogeneous on these bounds also. So because this V is here, and we have our 0 boundary conditions over there, this goes away and that goes away. So we're just left with this guy here. And our definition that we get of this Sturm-Liouville form from separation of variables shows us how do we define x double prime. So it's always nice to write that out, just to remind you, because as you change coordinate systems, that could be different. So we have x double prime is equal to minus lambda n squared x. So we can put that in this integral here, and we get what? 0 to pi minus lambda n squared x, I don't know how I forgot that, v dx. Now this is a constant, it's just n squared, so that comes out front. And now we're left with this here, this integral of our eigenvalue times v times dx, which was defined as our, that's the Fourier transform we're working with. So this just evaluates to minus, and because lambda n is just n, I'm just going to switch over to n squared, and we get a v hat n. So bringing it all back together, from here we get d vn dt. Now we're just going to bring this over to the other side, plus n squared vn is equal to, and then we have to worry about our third integral here, which I guess I'm going to have to do back on the first board. But this governing equation here is very simple to solve, right? There's nothing to that, it's just a, yeah. So, I guess we don't need this either. All right, so we have what? The integral of this. This is 3.
CD.
Yes.
So this is kind of a nice toy problem, which I don't know if that bears any physicality, but whatever. So we get e to the minus t, which is constant, so we can actually pull that outside of our integral. This is sine of nx times sine of 3x dx. So very quickly you should know, this is just our eigenvalue, or vector. This was the forcing function, and we can kind of just, you know what this is going to evaluate to.
Is the double dx intentional
Double dx?
in your sign?
Oh yeah, I don't know what that is.
Okay.
Yeah, so this is, if n is not equal to 3, this is 0, right?
Yeah.
And if n is equal to 3, it's 1. So we have 3 is equal to 0, n does not equal 3, and it's equal to e to the minus t for n is equal to 3. Because that was the constant sitting out front. And that's just from orthogonality of signs. So now we have our whole equation is this jazz here of d, v, n, dt plus n squared v n, am I doing this right? Yep. Equals, that's a bracket, 0 or e to the minus t, and I'm not really worried about those. So we get 2 equations. This is for 3, so we could do it for 0 for that, and then the other one you have to solve. So this one's very easy to solve, right? And then the other equation you'll get is so n is equal to 3, so that's squared. Yeah. So those are the 2 problems you solve. And once you have that, you're basically, that's it. So for this, you get something like, what is it? Vn is equal to an 0. And then for this one, we get something like, and I do not want to have to do these over again because it was a pain. So this is, I guess that's V3. And then you'll just, that's, AN is dictated by whatever our initial conditions are, which I'm not defining because I don't want to have to solve that part of the problem, because I only have so much time. I want to get on to another thing. So AN of 0 is equal to what? Just that integral.
So the 3 that you have when you were solving the circled 3 integral,
Yeah.
when you have the 2 different answers depending on the n value, is that 3 equals, is that a constant 3 or are you representing the integral 3?
This here?
Yes.
No.
That's the constant 3.
No, no, no.
In the middle, that's integral 3. Yeah.
Okay, so it's not the number.
It's not the number 3. No.
Now, the equation you just wrote on the board for A and naught, is that a given form or is that a form?
Yeah, that's the form of a Fourier transform. So this
Oh.
is
Sorry,
our eigenvalue,
yeah,
right? So this is x. This is our initial condition of u, which is just f of x minus our shift to make sure we're homogeneous. So like, let's pick a really cool f of x
1,
is x by pi.
okay.
Yeah. So we can solve that really quickly. Gives us zeros. That means it's kind of quiescent here, and then something's happening there with 2 different hyperbolics. And then you bring this out by multiplying, so then, v and is equal to the summation of, what is it, like a n? I wrote the definition earlier. A n of t times x. And you just sum all of them up.
So when you say an of 0, is that x is 0?
That's that's time is equal to 0.
Okay.
Yeah. An here is the time variable. So I very quickly wrote a definition of, what is it? V is equal to the summation of an of t x 1. So, not much is going to change when we go into 2 dimensions. You'll get another term like this, but your x, a second term like this, but you'll have a derivative in like another coordinate system. So we could try doing that, and then we can add a time, well, let's start creating it, and we'll see what people like, and we'll see if I can do it.
So will it be integral based off of the x domain, so dx, or would you have then a whole other problem with integration by dy?
Yeah, you get a whole other problem there.
Yes.
So I probably should have not refreshed myself on this stuff at 8 in the morning. But we'll see.
When you were writing out your an variable, the integral,
Yeah.
you chose f of x to be x over pi as an arbitrary, or did that show up somewhere else?
That'd be given to you. I just chose that because
Easy.
that means that your initial condition would be 0. Let me stop this and start a new video.